Okay, hey everybody. All right. Um, so let's take what we can understand about the Earth and the Moon, and see if we can't figure out more things about the other terrestrial planets, Mercury, Venus, and Mars. Mercury looks a lot like the Moon, right? Gray, heavily cratered, um, signs of old volcanism, but nothing recent. Um, Here are some close-up pictures of Mercury. Uh, it does look a lot like the moon, right? Heavily cratered, gray. The difference is that in between the craters, you've got some smoother surface, right? On the moon, especially on the highlands of the moon, in between the craters, there's more craters. Um, but on Mercury, the land is slightly smoother. And there are areas on Mercury that are kind of a lot like the Maria on the moon, right? Smooth areas that look like they've been smoothed over, paved over by lava flows. So if Mercury is a lot like the moon except a little smoother, what does smooth mean? Smooth means younger, right? Remember, rough means old, smooth means young. So if Mercury is a little smoother, then the surface of Mercury must be a little younger. Why would the surface of Mercury be a little younger? Well, Mercury is a little bit bigger than the moon. And if Mercury is bigger, that means it stayed hotter for a little longer. And so the volcanoes on Mercury were active for a little longer. And so those volcanoes were erupting, lava flowed, created new smooth crust for a little longer than the moon did, until eventually Mercury cooled off, stopped convecting, the volcanoes went dead, and then it started aging, and it kept on getting hit by even more impactors. So, Mercury and the moon are similar in size, but Mercury is a little bigger. So, it's going to be a little younger. Um, a lot of the new discoveries, most of the discoveries on Mercury in the last several years have been from the Messenger probe, which is a probe that NASA put in orbit around Mercury to study it all up close. Turns out that there is ice frozen in the craters near the poles. This is a picture of the North Pole on Mercury. And it turns out that there's water frozen in those craters near the poles on Mercury, much like there is on the moon. When I said in the last lecture that, people were sort of suspecting maybe there was ice in those craters on the moon, nobody was expecting this on Mercury. This was a shock because Mercury is the closest planet to the sun, right? The daytime on Mercury is 580 Kelvin, right? It is blisteringly hot. Water doesn't have a chance. Pardon me. Pardon me. Okay. Sorry about that. Everybody assumed that Mercury would be bone dry. And so when the Messenger probe went into orbit and started mapping the polar regions on Mercury, the fact that there is water frozen in those craters, in the craters it's 90 Kelvin, right? The parts of Mercury that are getting the direct sunlight, they're 580 Kelvin. But in those craters, down at the bottoms of those craters near the poles, it never gets sunlight. Sunlight never hits the bottoms of those craters. And so the temperature, there's no heat source there. There's no atmosphere on Mercury, so there's no greenhouse effect. Mercury geologically has totally cooled off. The only heat source on Mercury is direct sunlight, and those craters don't get direct sunlight. So the temperature at the bottoms of those craters is like 90 Kelvin. And any ice that's there just stays frozen, as apparently has happened. This is really telling us something. about maybe water in our solar system is a heck of a lot more common than we used to think, right? We spent a lot of time over decades looking around the solar system and saying, okay, there's water on Earth. Most of it is melted. Okay, um, there's water on Mars, right? But it's all frozen. We saw that when we talked about the atmosphere, and we'll see that a little bit more in a minute. Where else is there water in the solar system? Is water rare or is it common? Well, apparently water is a lot more common than we used to think, because there's water on the moon. There's water on Mercury, for crying out loud. Uh, Maybe water is much more common in our solar system. Liquid water is still rare, right? Liquid water we only find it on Earth, um, among the terrestrial planets. But maybe just the presence of water is much, much more common than we used to think. And if that's the case in our solar system, then maybe that's common in other exoplanet systems. And that makes the likelihood of finding liquid water on some terrestrial exoplanet much more likely and much more exciting. So this was a big surprise, but it might have larger implications than just, hey, look, ice on Mercury, neat. I don't know. This is still an open question. We still haven't found liquid water on any other exoplanets, but maybe it's more common than we used to think. I don't know. That's something, keep an eye out for news reports and discoveries that are made in the next few years, because maybe there's some room for some big surprises. Let's hop over to Venus. Remember that Venus is completely covered in clouds. So when you take a picture of Venus, it's just going to look like this, right? You're just going to see the cloud tops. If you see a picture of Venus and it looks like this is not a photograph, right? When we map the surface of Venus, this is not a picture taken in the visible spectrum. This is a radar map, all right? What that means is that we have sent probes out to Venus. This was one of the first big ones. This wasn't the first mission to Venus, but this is the first big mission to Venus. In '89, the Magellan probe went into orbit around Venus, and Magellan had a radar array. What is radar? Radar is where you send out a radio wave, and you have a radio wave bounce off of something and come back to you, and you can use the time of flight. You can use the time that it takes to send out the signal, have that signal bounce off and come back to you to figure out things like distance. Right? This is how radar, works when you're finding planes. Or aircraft or something, but you can also use this to measure the topology, right? So the Magellan probe was bouncing a bunch of radio waves off the surface of Venus, and by bouncing those radio waves off, you can get a map of the texture. You can get a map of the elevation of Venus. And so that's what you're looking at when you're looking at a map like this. This is not a photograph. This is not a map of color. This is a map of texture. This is a map of the topology, the shape of the surface of Venus. So there's a color code here. All right. When you look at these radar maps of Venus, the color code works like this. Dark means smooth and light means rough. All right. So these light areas over here are not light because they're light in color. That light is just a code that means this is really roughed up. The dark areas over here, and especially over here, but even over here, they're colored dark because that's the color code for smooth. So what is Venus like? Is Venus rough or is it smooth? It's mostly smooth. It's mostly the darker colored areas. So when you map the surface of Venus, that's the big surprise. There are not that many craters on Venus. Venus has the smoothest surface of any planet in the solar system. And smooth means what? Smooth means young. Venus has the youngest surface of any planet in the solar system. Because what smooths over the surface of a planet? Volcanoes. Venus is extremely volcanically active. Venus is about the same size as the Earth is, remember. So Venus is still hot. The inside of Venus is still molten and convecting, and that convecting molten magma erupts out of volcanoes. Venus is constantly resurfacing itself. When those volcanoes erupt, they pour lava across the surface. And if that lava flows across the surface, it fills in any old impact craters. So the impact craters that you find, there are a few impact craters. Mostly big ones, because in order to get through that thick Venusian atmosphere, you got to be a big rock to survive falling through the atmosphere of Venus and then still have some substance left to hit the surface. So the few craters that you find are these really big ones, and these craters must have been made fairly recently, because, like I said in the last slide, the whole surface of Venus is between 500 million and 1 billion years old. That's it. That's fairly young. The oldest parts of the Earth's surface are 2.5 billion years old. So the surface of Venus is much younger. All of the craters, the only craters that exist are the big ones that have been made in the last billion years, which is not many. What you do find are a lot of these volcanoes. And the volcanoes look different on Venus than they do on Earth, because these volcanoes look wide and flat. They sort of look like cylindrical pancakes. The name for these are called pancake domes, because when these volcanoes erupt, remember what I said last time about how the crust of Venus is thick and hard and brittle. So when you have magma building up under the surface of Venus, that magma builds up and builds up and builds up. And when these volcanoes erupt, they don't erupt like the Hawaiian Islands or something, right? They don't erupt in a big cone like it does on Earth. When these volcanoes erupt, the magma forces its way up through that thick crust, and it causes the crust to fracture. And so around these volcanoes, you end up with these rings of broken crust where the magma has broken through, and then once that magma breaks through that thick, hard crust, that magma finds a crack, it oozes its way up through the crack, and then it just pours across the surface like pancake batter. And so you end up with these wide, shallow volcanoes of just a volcano erupting and the lava oozing across the surface constantly, steadily. These volcanoes are just constantly erupting, flowing lava across the surface and recovering Venus in a new layer of lava about every billion years. This is the other reason why Venus's crust is so thick, is because the old crust doesn't get subducted. Venus doesn't have plate tectonics. And so the old crust doesn't get recycled back into the mantle by subduction the way it does on Earth. When new crust is made, it just pours over a new layer on top of the old crust, and it makes the crust that much thicker. And then the new, and then the volcanoes erupt some more and lay down a new layer on top of that, and a new layer on top of that, and a new layer on top of that. Like I said last time, the reason why Venus doesn't have plate tectonics is because it doesn't have water. It's the water on Earth that mixes into the rock, and it makes the crust of the Earth flexible and malleable, so that you can break the crust up into those nice thin tectonic plates that can slide around and crash into each other and build up mountains, or slide under each other and subduct. Venus doesn't have any of that. How can that be? How can it be that there's water on Earth, there's water on the moon, there's water on Mercury? Why isn't there any water on Venus? And the answer is, there probably used to be. There used to be water on Venus hey, Earth and Venus are so similar. Earth and Venus are about the same mass, they're about the same size. Why is it that Earth has these big oceans and Venus doesn't have any water? The answer is that it probably used to. Venus used to have liquid water, but Venus is too close to the sun. Venus was born with this thick carbon dioxide atmosphere, lots of volcanoes. When those volcanoes erupted, what comes out of volcanoes besides lava? Carbon dioxide and also water vapor. So when Venus was young, it probably had water. A lot of that water was blowing out of volcanoes, and carbon dioxide was blowing out of volcanoes. And if there's one thing we know about carbon dioxide and water vapor, they're strong greenhouse gases. So Venus had too strong of a greenhouse effect because it was blowing out all those greenhouse gases, and because it was closer to the sun. The greenhouse effect on Venus made Venus too hot. And since Venus was too hot, the water couldn't condense and fall as rain. It was too hot for rain. The water could never liquefy. It could never condense. It just stayed as water vapor. And so as those volcanoes erupted, Venus's atmosphere got thicker and thicker and thicker, and the greenhouse effect got stronger and stronger, and the temperature got hotter and hotter, and the water could never cool off. Venus could never cool off. You need liquid water. You need the water to condense as raindrops and fall as rain, because you need the rainfall and you need the liquid water to scrub carbon dioxide out of the atmosphere. And you need to scrub carbon dioxide out of the atmosphere to cool the planet off. Venus couldn't do that. Because the water just stayed as vapor in the atmosphere, the carbon dioxide stayed in the atmosphere, and Venus got hotter and hotter and hotter, and the volcanoes kept on erupting, and the atmosphere got thicker, and the planet got hotter, and that water vapor was just sitting there. That water vapor was just hovering in Venus's atmosphere, getting baked by sunlight. And what happens to water vapor when it's getting baked by sunlight is it's going to get hit by the ultraviolet light from the sun. Because again, Venus is closer to the sun. The ultraviolet flux is more intense on Venus than it is here on Earth. And so you've got these water molecules baking in the sunlight, baking in the ultraviolet light from the sun, and those ultraviolet photons have enough energy. Those ultraviolet photons have enough energy to break up the water molecules and turn it into hydrogen and oxygen. The hydrogen can blow away, and the oxygen can grab onto other molecules and have chemical reactions and stay in the atmosphere. So this is what happened to the water on Venus. Venus used to have water, but it was all water vapor. And then gradually that water vapor got destroyed by sunlight, by the ultraviolet light from the sun, until all the water was destroyed. And then Venus became bone dry. Right? Venus, once upon a time, Venus might have had all of the ingredients to complete the carbon cycle. But Venus was too hot. All the water evaporated, it stayed a vapor. You broke the cycle, and once you break the cycle, you can't get the carbon dioxide out of the atmosphere. This whole time, Venus's volcanoes were erupting and erupting and erupting, and the carbon dioxide just stayed in the atmosphere, and the atmosphere got thicker and thicker and thicker. This is why we say Venus has a runaway greenhouse effect. Because the greenhouse effect heated the planet up, and the planet has no way to cool itself off, because there's no way for the water vapor to condense and fall as rain. So that all that carbon dioxide stuck in the atmosphere. This is why Venus has an atmosphere 90 times thicker than the Earth's. Because Earth has a way of getting gas out of the atmosphere, getting the carbon dioxide out via the inorganic carbon cycle. Venus can't do it. And so Venus's atmosphere just got thicker and thicker and thicker, and the volcanoes kept on erupting and erupting and erupting until today the surface of Venus just is one giant lava flow. This is what the surface of Venus looks like. It's black with smooth lava flows, lava rock. You're not going to find water erosion because it can't have liquid water. You're not going to see that much wind erosion because the wind on Venus doesn't blow that hard because Venus isn't rotating that fast. This is why Venus is so uniformly smooth. It's all about the same age. It's all between 500 million and 1 billion years old because 1 billion years ago was the last time Venus laid down a new layer of lava. And it's been laying down the new surface for, the last 500 million years. Mars is quite different than Venus, because whereas Venus is sort of almost uniformly smooth all over, Mars has a lot of detail. Mars has a lot of geologic things going on. Although you wouldn't know it from looking at a satellite photo like this, because everything on Venus is covered in a layer of red, rusty dust. Remember we talked about the dust storms when we talked about atmospheres, right? Every time a dust storm covers Venus, it lays down a new layer of dust and kind of covers over all the details. But when you look at an elevation map, there's a lot going on. Mars is a planet of extremes. It's got extremely deep craters and extremely high mountains. And Venus is, I keep saying that, Mars is, you could sort of roughly divide it into two big areas. There's the northern plains, which are lower in elevation and smooth means young. And then you've got these southern highlands that are kind of like the highlands on Earth, high in elevation, rough, old. The southern highlands are the old part, again, because, it's old because it's rough. But we know about how old. We know that these highlands date back to about 4 billion years ago because when we landed the rovers, the Spirit and Opportunity rovers there in 2004, yeah, that's right, 2004, I think. We landed them near the highlands so that we're in the highlands so that we could measure those rocks and get their ages directly. There are these big impact craters, these big impact basins, the Hellas Basin being the biggest and deepest one. Lots of small craters too in the highlands, and there are some craters in the northern plains also. One of the tantalizing things when we started taking these good quality maps of Mars is that when you look at the debris that got shot out of the crater, the term for this is called ejecta. I don't think we've used this in class yet, but when you look at the debris that gets shot out of a crater, the term for this stuff is called ejecta because it got ejected from the crater. On bodies like the Moon and Mercury, the ejecta looks sort of powdery, like because it's made of that regolith stuff. On Mars, it looks kind of thick and splashy. And you'd go, well, what could there be on Mars that would make the surface rock look kind of muddy? Well, gosh, what does it take to make mud on Earth? Water? Could there be water on the surface of Mars, making that topsoil look thick, kind of heavy? That's interesting. This big area here is called the Tarsus bulge, and this is a big series of mountains. And why are there mountains there? Because they're volcanoes. Each of those peaks is a volcano that has been driven up by the eruptions of magma. Also on the Tarsus bulge, you find what's called Valles Marineris, this giant canyon system from where the crust split. Valles Marineris is huge. Here's the Grand Canyon for scale. I just wanted to put these side by side. Here's the Grand Canyon, on Earth. Here's Valles Marineris. Valles Marineris, this canyon system, is 4,000 kilometers long, so it's about the length of the United States. It's 200 kilometers wide, and it's 7 kilometers deep. 7 kilometers is what? About 5 miles. So the Grand Canyon is about a mile deep from rim to floor. This is the length, the Valles Marineris is the length of the United States, and it's 5 miles deeper, 5 times deeper than the Grand Canyon. It is huge. The biggest of these shield volcanoes on the Tarsus bulge is what's called Olympus Mons. This volcano is 700 kilometers across. It is, it's big enough that it could cover the state of Arizona, and it's 27 kilometers high. The Mount Everest is 9 kilometers high, so it's 3 times higher than Mount Everest, right? It is so high, the top of this volcano is so high that it's peeking out above the atmosphere. This white stuff is the clouds. The top of this volcano sticks out of the atmosphere of the planet. That's how tall this thing is. When I say shield volcanoes, I mean, there are, again, those of you that have taken a geology class, well, there's different kinds of volcanoes. How do you get a shield volcano? Well, on Earth and on Mars, a shield volcano is what you get when you have a giant magma chamber, a big chamber of magma underneath the crust that builds up. The magma builds up and builds up and builds up until the pressure gets so high that the magma erupts through the crust, drives up the tectonic plates, and then the magma pours across. And when the lava pours out of the volcano, it builds the volcano up bigger and bigger and bigger. This is how you get the Hawaiian Islands here on Earth. The Hawaiian Islands are shield volcanoes. The difference between the Hawaiian Islands and the Tarsus volcanoes on Mars is Earth has plate tectonics. And so over time, as the tectonic plates move, every time there's a major eruption of this magma chamber at the bottom of the Pacific Ocean, you have that magma force up a volcano, and then the crust moves, and it forces up another volcano, and the crust moves, forces up another volcano, and the crust moves. So this is why the Hawaiian Islands are in a chain like this, because as those volcanoes are forced up again and again and again and again, the plate moves. The magma chamber doesn't move, but the plate moves so that every time there's an eruption, it pokes up another volcano, another one in line. There never was plate tectonics on Mars, so that every time this magma chamber underneath the Tarsus bulge erupts, it just forces up the same crust over and over and over and over again until that crust gets forced up so much that this entire side of Mars has buckled. This entire side of Mars is bulging up above the rest of it, and then on top of that bulge, you end up with those volcanoes erupting. When you forced up the crust, it split the crust, and so you end up with this giant crack. And then when that crust split, I mean, it's like baking bread, right? When you bake a loaf of bread and that bread rises and expands in the oven, eventually the crust of the bread is going to split. To relieve the pressure, basically. And then after the crust split, sorry, not the crust, the crust. Sorry, I'm talking bread and planets here. After the crust of Mars split, that created a channel. It created a canyon, and then through that canyon, lava flowed. So that when those volcanoes erupted, lava's going to roll downhill. That lava is going to flow downhill into this canyon and then flow out into the northern plains, because that lava is going to flow downhill. That lava flowed down into the northern plains this way, that way, and this way, much like the Maria on Mars, or much like the Maria on the moon. That lava flowed down into the northern plains and laid down new smooth crust. Then the lava stopped flowing, but even after the lava stopped flowing through those channels, then water kept on flowing. Because when you look at these outflow channels, when you zoom in and look at these outflow channels today, these do not look like lava beds. These don't look like they were carved by flowing lava. These look like they were carved by flowing water. How can you tell the difference? Well, when lava flows, lava creeps, right? Lava is viscous and sticky. And when lava flows, it just covers over everything and leaves a flat, smooth crust. When water flows, water is low viscosity. When water flows, it flows quickly. And so when water flows quickly, it can carve rocks. It causes erosion. It can leave islands in the stream. And that's what you have here. When the lava stopped flowing, the water kept on flowing. There was, once upon a time, rain and rivers flowing through these outflow channels, and when that water flowed, it carved these boulders and carved these islands left in the middle of the rivers. On Mars, we know there's water on Mars today, right? We know that there's water, frozen as ice on the ice caps and stuff. But what these tell us is not just that there was water on Mars, there was liquid water on Mars. Mars can't have liquid water today. It's too cold, right? The temperature on Mars is 220 Kelvin. Water freezes at 273 Kelvin. Today, Mars is way too cold for liquid water, and yet once upon a time, there was so much liquid water that it could flow as a river and erode away these channels. Today, these channels look like dry riverbeds because that's exactly what they were, or it's exactly what they are. Some of these answers about, what is Mars like today? What did Mars used to be like? There's only so much that you can do from looking at a distance. Sometimes you really got to get down onto the surface and look at what things look like up close and personal so that you can see it in more detail. And this is why we've sent 3 big generations of robots to go and roll around on Mars and sniff the rocks and see what they're made of. See what it really looks like down there on the surface. So here's the first rover. This little guy here is the Mars Pathfinder that was landed in July 4th, I think it was. It was the 4th of July, 1997. This is what the 2 twin rovers, Spirit and Opportunity, they both were this model. And then here's the new big toy. Here's what the Mars Science Lab, or what's called the Curiosity rover. This is a new big thing that can move a lot faster because it's got bigger wheels and more powerful motors. And also because this thing is bigger, you can pack more instruments onto it. So the Pathfinder is long dead. Spirit and Opportunity, they lived a good long life, and they finally got switched off. They finally reached the end of their mission just a few years ago. The Curiosity rover is still going strong, making all kinds of new discoveries on Mars. So we definitely don't have time to go over all of the things that these robots have discovered because that's a whole class unto itself. But I'll hit some of the high points here. One of the first things that the Spirit rover did is it drove into this crater, and one of the things it discovered is that there are these horizontal deposits of salt minerals at the bottom of this crater. Now, how do you do that? How do you get horizontal sedimentary deposits of salts? Well, first off, you've got to dissolve the salts in some kind of a solvent. What liquid do we know of is good at dissolving salt? Water. So you take salt, you dissolve it in water, and then you let that salt settle out of the water and build up on the floor of the lake. That's basically what we're looking at here. This crater used to be a giant lake. And then as the salts settled out of the water, they built up and built up and built up layer by layer by layer. And then when all the water was gone, the salts stayed around. Not just water. It has to be liquid water. Have you ever tried dissolving salt in ice? It doesn't really work that well. It's got to be liquid water. After that was done, they rolled the Spirit up to the top of this hill and started looking around and taking a panoramic view of the horizon from the top of this hill. I just threw this in here because it's awesome. Here's the Vista. Here's the landscape of a totally alien planet taken from the cameras of the Spirit rover. No, I just threw these in here because they're awesome. On the other side of the planet, the Opportunity rover found layers of hematite. What is hematite? Hematite is an oxidized iron mineral. Well, gosh, what else do we know that's good at oxidizing iron? Also water. A few years later, just a few years ago, they were cruising the Opportunity rover, and they saw this little white streak on the ground. And so they had the rover take its little rock sniffer and go and sniff. Hey, what's that white streak made of? And it turns out that white layer, that white streak, is a seam of gypsum. Gypsum is the stuff that you make cement out of. What is gypsum? Gypsum is a hydrated calcium mineral, right? How do you make cement? If you've ever poured cement or if you've ever made cement, what do? You take, you buy a big bag of calcium and gravel, you pour it into your cement mixer, and then you add water to it. And what do? What happens? The reason why you need a big cement mixer is because you got to mix a lot of water in with that calcium. Because as soon as you pour water into the calcium soaks up all the water and then it dries out again. So then you got to add more water and churn it some more, and it soaks up that water. And you add some more water and you churn it some more, and it soaks up that water. In order to take calcium dust and gravel and turn it into pourable liquid cement, you need to mix a lot of water, because that calcium grabs onto those water molecules and locks them up as gypsum minerals. And then you pour out the cement, and you pour the cement, and you let the cement cure and harden, and the calcium and the water minerals lock up together as rock, as gypsum rock. Gypsum, by definition, is a hydrated calcium mineral. It is calcium mixed with water. A little bit of water? No, a lot of water. Just like it takes a lot of water to make cement, it takes a lot of water to make gypsum minerals. And this seam of gypsum that Opportunity discovered was found at the bottom of another crater, what they named the Endeavour crater. So this crater also, on the other side of the planet, right? Spirit and Opportunity were landed on opposite sides of Mars, and yet they both found craters that used to be filled with liquid water. It's the only way to explain the minerals that you still find on Mars today. But I said a minute ago, the new big toy on Mars is the Curiosity rover. And they landed Curiosity in this Gale crater. And the Gale crater, here's the crater floor. So the crater is really big. It goes all the way across. And in the middle of the Gale crater is this big hill. This hill is inside the middle of the crater. And if you look carefully, what's the hill made of? This hill is made of horizontal layers of sedimentary minerals. What is sedimentary? Sedimentary rock is the kind of rock that you get when you take minerals, you mix them up in water, and then you let the minerals settle out of the water. One of the first big discoveries made by the Curiosity rover when it went rolling around the Gale crater is that you found these rocks here. They don't look like much, right? These don't look like terribly flashy. But what you're looking at are what are called sedimentary conglomerates. Basically, you have a bunch of pebbles and a bunch of gravel cemented together, glued together by minerals that settled out of the water. The only way to make these kinds of rocks is if you have a bunch of gravel sitting at the bottom of a very large body of water, and then as minerals settle out of the water, as minerals sediment out of the water, they get in there among the gravel and glue the whole thing together. This crater, now the fact that this whole hill is made of sedimentary rocks. It means that this big crater didn't used to have a little bit of water. This crater used to be a big lake. And this is a pretty big crater, so I don't know if you call it a lake or a sea. If you wanted to find rocks like this, it's pretty easy. Go climb Camelback Mountain. Go climb any of the hills in the parks around town here, because Camelback and the whole area, this whole part of central and southern Arizona, is filled with rocks like this, because this whole part of the world used to be at the bottom of a giant inland sea. The ground that you're standing on right now used to have a mile of water on top of you, because this whole part of the world, 1 or 200 million years ago, we all used to be underwater. All this land used to be the bottom of an ocean, the bottom of a sea, and therefore all of these rocks that you see around the valley here you find a lot of these sedimentary conglomerates, right? Pebbles and gravel that got cemented together at the bottom of the sea. And then because of plate tectonics, because of continental drift, this part of the world got lifted up out of the water, all the water rushed away, and the rocks are still left behind. All of this evidence is pointing to one giant conclusion. That the question 20 years ago was, is there water on Mars? And today we know definitively there is a heck of a lot of water on Mars. It used to be liquid, but now it's all frozen, right? Today, we saw this before, right? The water on Mars is frozen at the ice caps. You also find a lot of ice frozen on Mars as frost in places like this. So here's this whole blanket here is a blanket of frost frozen around this big hill on Mars. Several years ago, the Phoenix lander, which is not a robot. It is a robot, but it's not a rover. It doesn't have wheels. It just landed on Mars and then studied the area right around the lander. They landed this Phoenix lander. The Phoenix lander had this big shovel here, and what they did was they dug a trench. They dug a trench just, a few inches deep, just to see what's the soil like. What's the ground like right underneath the surface? There's this frost, this white frost, and when they dug this trench, there's these few pebbles right there. You're like, well, what are those pebbles made of? Well, you come back a few days later, the pebbles are gone. They've evaporated, and this frost has started evaporating too. There is frost. There is ice frozen right underneath the surface all over Mars. Right? The ice on Mars is not just limited to the poles. Apparently, it's all over the surface. The question is, why is it frozen? Right? That's a big question there. The water on Mars used to be warm and liquid, and it would flow through rivers, and it must have fallen as rain, and it pooled in craters for a very long time. But then eventually Mars froze, and all the water froze. What happened? What happened is the dynamo stopped. I'll come back to this slide in just a minute, just so you can read it better. But back billions of years ago, Mars was still hot. Mars was still convecting. Inside Mars, the magma was still convecting. And while the magma was convecting, the lava was erupting out of volcanoes. Back when the volcanoes were erupting. We know there were volcanoes on Mars. We can see the volcanoes today. They're dead today. But the volcanoes used to be active on Mars. And when the volcanoes erupted on Mars, those volcanoes were pumping CO2 into the atmosphere. But while Mars was still hot and convecting, Mars also had a dynamo. Mars could create a magnetic field. The magnetic field was being created by Mars, and when Mars had a magnetic field, Mars's magnetic field protected it from the solar wind. Right? What is the solar wind? The solar wind is this breeze of particles, hydrogen, helium, electrons, blowing off of the sun. They're charged particles, and charged particles can get deflected by magnetic fields. So here on Earth, we don't get a lot of the solar wind because Earth's magnetic field protects us from the solar wind, and that, it turns out, is a very good thing. Because what can the solar wind do if it hits the atmosphere? It can strip it away. The solar wind used to get deflected away from Mars because of the magnetic field. But then, eventually, Mars cooled off. And when Mars cooled off, the magma stopped convecting. And when the magma stopped convecting, the magnetic field collapsed. And when the magnetic field collapsed, Mars became vulnerable to the solar wind. The solar wind blew in and slowly but steadily started stripping the atmosphere away from the planet. When Mars had a magnetic field, Mars's atmosphere was thicker with carbon dioxide that was blowing out of those volcanoes. And if Mars, not if, I don't think it's much of an if. Today we know pretty confidently. While Mars was still hot, Mars's atmosphere was thick with CO2, and if Mars's atmosphere was thick with CO2, it had a stronger greenhouse effect. When Mars had a stronger greenhouse effect, Mars was warmer, and it had more atmospheric pressure. And if you've got a planet that is warm enough and has enough atmospheric pressure, you can have liquid water. That's how the water was able to stay liquid. That's how Mars was able to stay warm and wet for billions of years. But Mars is smaller than Earth, and that means it cooled off in less time. A couple billion years ago, Mars cooled off, the magma stopped convecting, the magnetic field collapsed, and when the magnetic field collapsed, the solar wind blew in and was able to knock those gas molecules until they reached the escape speed and they just blew away. When Mars's atmosphere started blowing away in the solar wind, the atmosphere got thinner and thinner and thinner. The greenhouse effect got weaker and weaker and weaker. Mars got colder and colder and colder until all the water froze, and it's stayed frozen ever since. That's how Mars changed. That ancient Mars versus modern Mars changed because Mars is smaller and it cooled off in less time. That's probably pretty close to the right answer. Are there still some questions left to answer? Sure, we haven't solved all the mysteries of Mars, but that's probably the big answer. The reason why Mars used to be warm and wet and geologically active is because it was hot back then. But today, Mars is cold, geologically dead, frozen, and dry. There you have it, right? Venus, Earth, and Mars were born very similar. Venus, Earth, and Mars were born with a carbon dioxide atmosphere and water. But Mars got too hot, and it stayed too hot. Earth was able to keep the inorganic carbon cycle going so that Earth could cool itself off and stay a nice moderate temperature with liquid water, which is why you and I are here right now. Mars was warm with liquid water. Mars had a carbon cycle for a while, right? Mars had volcanoes, but Mars could also cool itself off in rain, and there was rain in rivers and lakes for a while. Mars was very Earth-like for a while, but Mars was cooler. Sorry, Mars was smaller than Earth. Mars is smaller than Earth. And because Mars is smaller, it took less time to cool off, and when it cooled off, the planet froze, and it's stayed frozen ever since. 3 planets that are basically identical. They were basically identical 4 billion years from now, or 4 billion years ago, and then over the last 4 billion years, they've evolved so that each of them is different and unique in their own ways. All right. So hopefully that's made some sense to you, because the next exciting thing, well, in science, is what about the alien planets, right? Now that we've got a handle on what planets are like, now that we've got a handle on what terrestrial planets are like in our solar system, now we can start trying to do some bigger conclusions and say, okay, now that we've discovered terrestrial exoplanets, now that we've discovered terrestrial rocky metallic alien planets, now we can start saying, well, what are they like? Well, we don't know. I mean, the honest answer is we don't know yet. But we can start doing some educated guessing and saying, okay, if you discover an alien terrestrial planet, is it more like Venus? Is it more like Earth? Or is it more like Mars? Because if it's more like Earth, is there liquid water? Is there a carbon cycle? Is there life? And that's the big burning question that we all want answers to. So that's part of what the homework is going to get at for you, and that's part of what the final project is going to get at, is to say, okay, let's take what we know about terrestrial planets in our solar system and try to make some smart guesses as to what an alien planet might be like. So that should help you out with the project. Have a good one. Take care. If you've got some questions, bring them into the live chats. Can't wait to talk to you guys. I hope you're doing well. All right. Take care, everybody.